Okay. Okay. Um, Good afternoon to everybody. Thank you so much to be here in next great afternoon today with an exceptional speaker, Professor Claudio Gorodski from the University of São Paulo. Let me briefly introduce Professor Gorodski, but well, for many of us, he's a very well-known mathematician, but he's at present full professor of the Department of Mathematics of the University of São Paulo in Brazil, working in differential geometry mainly. And he received his PhD from the University of California at Berkeley in 1992, and his habilitation degree at the University of São Paulo in 6 years after that. His research interests include the Lie transformation group, the Riemann geometry, the geometry of submanifolds, and the Riemann symmetric space and sub-Riemann geometry. And he is at present one of the two editor-in-chief of a beautiful journal, which is the São Paulo Journal of Mathematical Science. And he's today with us to give the following talk, which is a question. Can no trivial isometric equation of the unit and its sphere be made arbitrarily small? Okay, thank you so much, Professor Claudio. Time is with you. Use freely because we don't have a limit.
Ah, okay, thank you very much, Kinya. It's a very kind introduction. Thank you very much to you and to Renato for this uh, very nice invitation to participate in this seminar. I'm honored. So, I'm going to talk about joint work with these people, Christian Lange, Alexander Lichak, and Ricardo Mendes. And in fact, this is not a very recent work, but I chose this topic because I thought it would be more appropriate to this audience. And so the, the question is this. We consider unisphere, and let me see how to. Yeah, we consider a subgroup of the isometry group of the unit sphere. Any subgroup, finite, infinite, connected, disconnected, doesn't matter. And then we want, well, let me recall some basic definitions, some basic concepts. So if you take a point, we have the orbit of this point under this group G. So we just apply all the elements to P and we get a subset of the unit sphere. This is an orbit. Um, for instance, if G is Lie group, then this orbit is going to be a smooth submanifold of the sphere. And the isotropy group is the subgroup consisting of all elements of G that fix P. So this is going to be a closed subgroup if we have continuous action here, right? Um, and, and there is an identification between this quotient and the orbit. Okay, so and the spaces of orbits is the set of all orbits of this action, and it has the structure. In principle, it's a pseudometric space. I mean, the distance between 2 points in X, take 2 points in X, they correspond to two orbits upstairs in the sphere, and we just take the distance between these two subsets, okay? So it's the infimum of the distances between points in the two orbits. Have two orbits. Oops. P, P and Q. These are the orbits. And why it's pseudo in general? Because if these subsets are not closed, then you can have distance zero, but they are not the same orbit. It can happen, right? So that's why it's pseudo. But in case G is closed, then it's a genuine metric, because then it's going to be compact, and these orbits are going to be compact too, and then distance for two different orbits, we're going to have a positive distance. And in fact, this distance is going to be realized by a geodesic segment which is orthogonal at the endpoints. So this is a geodesic in the unit sphere. It's an arc of a great circle. Realizes the length of this arc is going to be precisely the distance between the two orbits in this case. And finally, we define the diameter of X as usual to be the supremum of the distances between 2 points. So in this case, this supremum is going to be attained because X is compact. And we note that the diameter of X is going to be zero if X is a point, for instance. X is a point means that there is only one orbit, so from one point I can reach any other point using an element G. So we say that the group is transitive on the unit sphere in this case. So the orbit space in this case is going to be just 1 point. And of course the diameter of 1 point is zero. But also if G is not closed, I mean, you could have a dense orbit and then again the diameter would be zero, right? So the main question, the main problem is we want to know how small diameter can be if it's not zero. That's the main question. So let's make additional remarks. So in general, the diameter does not change. It's an easy exercise to show that if you replace G by its closure in the orthogonal group, the diameter is not going to change. Therefore, it is no loss of generality to assume that G is closed from the outset. And then we have really a metric space in the orbit, a metric structure in the orbit space. And a closed subgroup of the orthogonal group is a compactly group, and because any closed subgroup of a Lie group is a Lie group, and in this case it's even compact. And also there is this notion of Alexandrov space, because X is not really, in general, it's not a smooth manifold. It has singularities. I mean, because the orbits of G can have different dimensions and different types, and therefore this causes the orbit space to develop singularities. But so it's not really a smooth manifold, but it's going to be a smooth manifold in an open, dense set, connected set, and it has a very nice structure. In fact, there is this notion of Alexandrov space also. We don't need to get into details, but despite not being a smooth manifold, it's a very nice space, this X. And henceforth, we're going to assume that G is closed. Okay? So it's a compactly group. The orbits are properly embedded submanifolds. The distance is a metric distance. And now we know that for a closed group, diameter is 0 if and only if there is only one orbit. So this is kind of trivial case for us. We're not interested in this case. We want to consider non-transitive groups and see how small the diameter can be. So let's start with the case. The simplest case is the case of n equal to 1. This is a circle, right? We have this cyclic group generated by rotation of this angle 2 pi over k. This divides the unit circle into k arcs, right? So for instance, something like this, if k is equal to 6. And then this k is arbitrary, right? An positive integer. And the diameter is going to be the diameter, well, the length of the circle is 2 pi over k, and the diameter of a circle is always half, right, of its length. So the diameter is going to be pi over k, goes to 0 as k goes to infinity. So in this case, it's easy to make it go to 0. So we can make it arbitrarily small in this case. So let's move to the case n equal to. So here there's a classification of closed subgroups of O3. It's a short list. I mean, we have this. For instance, these are finite groups of isometries of Platonic polyhedra, right? And I mean, it's using linear algebra, one can compute the diameter of the orbit space, and then, of course, we can also have cyclic groups. Even for S2, we can rotate around an axis, right? We can also reflect along this on this plane. So if we rotate, I mean, it's interesting just to make some remarks here. So if you just rotate, then we're going to have two fixed points, and these orbits are just one point, right? They survive in the quotient in the orbit space. So in the orbit space, we're going to have a distance of pi between two points, and so the diameter is going to be pi if we have fixed points, right? But even if we reflect on this plane, then we identify these 2 points. They are the same, the quotient now. But still, we can go from this point to the equator, and then we get pi over 2 as diameter in the quotient, right? So we can see these diameters there. And, well, these are continuous rotations here, but we also have fixed points, so we get the diameter pi, or we can have a reflection again pi over 2. So it's very easy to see the explicit classification to understand. So we see that there's a lot more rigidity here than in the case of the circle, right? And in fact, well, this question, I mean, it was posed in a paper by these two mathematicians, Carsten Grove and Markovs, in the 1990s, how small the diameter of a non-trivial quotient unit sphere can be, right? And we showed that what we saw in the case n equal 2, in fact, this kind of rigidity is present for all larger dimensions, in the sense that there is a bound. So starting with n equal to any quotient of the n sphere by a group of isometries either has diameter 0 or diameter bigger than this universal constant epsilon, right? Um, so the novelty of our result resides in the fact that epsilon is independent of n, because I'm going now to talk about some previous results and related results and to put our result into context, right? Um, I mean, if anybody has questions, you can interrupt me at any time, okay? Let's see. Okay. So let me first talk about related work. So explicit lower bounds, in fact, bigger than one fourth, have been found for special classes of action by explicit calculation. So, like free actions, you have a free action of G on Sn, the quotient is going to be a smooth manifold in this case. And these are classified, the actions. So you can just go through the list and do explicit calculations. And this McGowan was also related to growth. And finite Coxeter groups. And in the case of a finite Coxeter group, the quotient is going to be an orbifold, a Riemannian orbifold. So also you have a classification there. You can go through classification, make explicit calculations. And then also quotients of dimension at most 2, 1 and 2 are classified, and you can do explicit calculations in this case. So this is maybe more interesting. I mean, Sarah Greenwald, 2000, she derived non-explicit dimension-dependent lower bound. So this bound depends on n. So she fixed one sphere and so and fixed. She considered subgroups of the isometric group, and then the main idea is that if you have a sequence of groups whose diameter goes to 0, then she showed that this GI has to converge in some sense to a subgroup, and these are compact, so essentially semi-simple, and there are not too many semi-simple subgroups here. So up to conjugation, and if these are non-transitive, you cannot converge to a transitive group. So this is the main idea of her proof, but we cannot obtain our result from hers in principle because and a limiting argument, because there's a very nice example by Nick Weaver in Math with Flow, where he constructs a sequence of isometric actions with non-dense orbits on this Hilbert space, whose diameters go to 0. So for Hilbert space, the result would not be true, according to this counterexample. Yeah, I mean, on the unit sphere, right here. Yeah. And so let me say that this problem also has an application in control theory because independently from us, Gautier and Rossi published in 2021, they showed the existence of a dimension independent lower bound for, but only for complex representations of compact connected groups, and also they missed the spin representations. So, and these people they work in control theory, and they were. There is a conjecture of Agrashev related to the minimum time on quantum systems, and so this is related to controllability and reachable sets in control theory, and yeah. So this was independent work, but not for all groups, right? It's only for connected groups and only complex representations and and also mixed spin presentations. So even maybe more interesting than this Ben Green's 2020 Duke paper. After completion of our work, we learned that Ben Green on this paper on the width of transitive sets bounds on matrix coefficients of finite groups proved a very strong version of our result for finite groups only, with a much more complicated proof. So let me show the relation here. So, I mean, if we are in the unisphere, the spherical distance here is going to be the cosine of this angle, right? Central angle. So, and of course, this cosine is this inner product, right? But if you look at this inner product, so fix 2 points P and Q, and look at the orbit of P under G, this you recognize this as a matrix coefficient of this representation. And that's the relation here, bounds of matrix coefficients. So he shows that for all n, at least 2 and P, there is another Q such that the supremum of this matrix coefficient is bounded, yeah, by this number. So this goes to 0 as n goes to infinity. So this is an upper bound of matrix coefficients, but of course cosine is decreasing. So in this range, so we get a lower bound for the diameter. So since this goes to 0, the distance goes to pi over 2 as n goes to infinity. So in fact, he not only his result is strong in the sense that as n goes to infinity, the diameter of quotients of the unisphere by finite groups go to pi over 2, really. Not only bounded away from 0, but even going to pi over 2. And yeah. So if you look at this inequality that he got, I mean, he's saying that basically that as n goes to infinity, for any p, if you look at the orbit, for finite groups, right? There's a Q where this inner product is small, so they sit in a slab like that. Another way of interpreting his result. So, yes, this problem is very natural from the point of view of geometry, but it relates to many other things too. Oops, sorry, made mistake. I clicked something wrong here. Yeah. Yeah. Okay. Okay, let me, now I would like to to say a few words about our proof. How do we attack this problem? Um, Preliminary remarks. So this is kind of folklore lemma you can find in many different places. Um, if if you have a fixed point diameter pi, that's basically what we said before. I mean, you have a fixed point, then of course the action is linear, so the antipodal point is going to be fixed too, and these fixed points that survive in the quotients, they are orbits in the quotient, and in the quotient they're going to have distance pi. So, and if you have, I mean, of course you can, if you have a group like that, you have a representation on Rn plus 1, right? A linear representation, and the diameter is pi of 2 over 2 if and only if this representation, well, it has no fixed points and the representation is reducible. So if you decompose your representation into two invariant subspaces and you take points here and here, then the distance between these 2 points is going to be over pi over 2. I mean, this is going to be a minimizing geodesing, realizing the distance between these 2 points. And so the diameter is less than pi over 2 if and only if the representation is irreducible. This already shows that we need only consider irreducible representations, right? Otherwise the diameter is big. But we somehow refine this lemma using Schur's lemma, analyzing isotypical components, some elementary arguments. We show that if the diameter is less than or equal to pi over 4, then even every normal subgroup either acts irreducibly or super reducibly, which is the opposite. What I mean is that so subgroup is going to be called super reducible if the end representation is splits completely like that, where V is one-dimensional representation. And this depends on the type, if it's R, C, or H, for instance. So N is going to act, is going to be a finite group, really, up to scalars. So for instance, in the real case, it is going to split like this, one-dimensional real representations, right? And in each, so you can have just a finite group, maybe containing plus or minus 1, and yeah, just plus or minus 1 acting on each component here, or in the complex case, you have sum of C's, and your group is S1 acting here diagonally, right? And maybe, yeah. Or in the quaternionic case, you can have a decomposition like this, and you have S3 or SP1 acting as quaternion scalars there, right? Okay. So either it's reducible or super reducible, normal subgroup. And of course, we are only interested in groups realizing this. Otherwise, the diameter is big and we don't care. So what we do is we apply this refined lemma to the identity component of G. It's a normal subgroup. So G is compact already. We assume that. We can assume irreducible also. And the identity component is a normal subgroup, so we can apply the previous lemma. And so there are two main cases. Either this identity component is irreducible or it's super reducible, meaning that it's a finite group up to scalars. So could be a finite group, could be a finite group times S1 or a finite group times S3. Okay. So H finite or H S1 or H S3. Okay, or G0 is irreducible.
No. No.
So we argue separately in each case, and in both cases, the bulk of our treatment is group theoretic. We use finite group theory, we use Lie group theory, but we also use some Riemannian geometric arguments in an essential way. In both cases, finite and infinite. So, any questions?
Well, okay. Thank you so much to our speaker. Let me say something first. I'm come here as an analyst, which means that
Sure.
my geometric imagination is essentially Euclidean, occasionally compact, and usually complete under a norm. So I ask to the geometers in the audience for questions. Question or remarks? In the middle time, I have a curiosity. That
Yeah.
Sarah Greenwald, that related with the epsilon m positive, is the same Sarah Greenwald related with some joke in The Simpsons?
I'm not.
Some people working with the team of The Simpsons, the series.
I don't know. I mean, this was her PhD thesis under Karsten Grove, I think.
Probably that.
But I don't know.
Because I only know the name, but
I have never
some
met.
list of people working The Simpsons in a job
But
related
it's a
with P or
very
something like
common
that.
name. Maybe
But
it's a common name, right?
that well, but the job
I
are
never met her.
okay. Question or remarks? Serious question and serious remarks. Okay, if not question,
Okay.
no remark. Let me
So,
thank you so much, Claudio. First of
okay.
all, but please.
Yeah, let me continue then. So let's first analyze the case G is finite up to scalars. So since you have a finite group, but you can take a semi-direct product with some real complex or quaternionic unit scalars, right? That's our group. And we want to see how small the diameter of a quotient can be. And the presence of the scalars forces us to work with projective representations. This is something I didn't know about it, and I learned a little bit about it. But here, if there are no scalars, just a finite group, then we can just work with represent, usual representations. So here we're going to explain the simple geometric idea of our proof. In the special case, G is a finite group, so we do not need projective representations. So hence we assume G is finite. We can also assume it's a maximal subgroup, right? Because if you enlarge the group, you enlarge the orbits, you make the orbit space smaller, it decreases the diameter, right? So we can always make our group larger. Of course, we don't want to have a transitive action. This would give point in the quotient, right? But here, since we have finite groups, they're never going to be transitive, right? So we can always enlarge them. So we can assume G is finite, a maximum subgroup. In particular, since it's finite and maximal, the representations of a real type, there's no complex structure there. Otherwise, we could enlarge it with this circle generated by the complex structure. And so here we're going, the main idea is very simple, really. It's we compare the diameter and the volume of this orbit space. Okay. So first thing, if you have a group, finite group, let's say we reflect, we have this coordinate axis, and we reflect on these coordinate planes, right? So this would be like z2 plus z2 plus z2. What you get just this triangle, right? With right angles. And so, I mean, even, I mean, you can see very simple, it's very simple. In this case, you have a tessellation, right, of the two sphere with 8 right, well, triangles with right angles, right? And so this is precisely the order of this group, 8. And it's general, right? If you have a group of some order, you're going to tessellate this here by this number of domains. And in fact, so the volume is going to be just the quotient of the volume of the sphere by this cardinality of the group. So, because they're all congruent, they all have the same volume, right? This is clear. On the other hand, X is bounded, so if you take a sufficiently large radius, you can take a ball, and if you cover X, and the volume X is going to be the volume of this ball, right? I mean, of course, X is compact, you're going to have some redundancy also, but it doesn't matter. It will cover X. And now we use some classic theorem from Riemann geometry, Bishop-Gromov theorem. It's a comparison theorem. It says that if a space is more curved, if one space is more curved than the other one, the volumes of balls of the same radius will be smaller. So if the space is curved, like for instance, a Euclidean space, I mean, you have pi r square, right? And if you curve this, you take the same radius. I mean, this is going to have a smaller area now. So here, I'm referring to Euclidean space. So X is positively curved because it's a quotient of the sphere, which is positively curved. And when you take a quotient, the curvature always increases. So this is more curved than Euclidean space, like in this picture. So the volume is going to be bigger. And in Euclidean space, of course, we have this homogeneity. If you take a ball of radius d, then its volume is d to the n times the volume of the unit ball. So we have this homogeneity in Euclidean space. And are you following this line of argument, more or less? I hope so. So now we have this simple bound also, because if you, I mean, um, so here is the unit disk, right? This is the unit disk here. And this is the upper hemisphere of the same dimension. And of course, this is the lower hemisphere. So you have the full sphere here. And of course, if you project the upper hemisphere to this disk, you decrease the area or the volume, yeah, right? So we have this inequality here. The volume of the whole sphere of dimension n, unit sphere, is larger than the volume of the unit ball, right? And finally, we can put together these two, this equality and this inequality, we can put them together. And what we get is this. I mean, we're going to cancel this volume, right? And we get this inequality. And so if you have an upper bound here, we're going to have a lower bound for n, right? That's what we want. We want a lower bound for n. So we need an upper bound for this number. And then we take the logarithm of this number. It's easier to analyze the logarithm. Yeah. So what we have to do, we have to find an upper bound for the numerator. So upper bound. And a lower bound, right, for the denominator. And right, we do that. We use the classification of finite simple groups. So of course our group is not simple, okay? But first we consider the case of simple groups. If the group is simple, well, the classification says there are 4 classes of finite simple groups: cyclic, alternating, Lie-type, and sporadic. And so we can work directly with these 2 classes. They are not complicated groups, and there's a lot known about their representations. And also, groups of Lie-type are classified. There are tables for their representations of minimal dimension, right? And we can use all this explicit information. And fortunately, we don't need to worry about these monster groups, sporadic groups, because they are finite in numbers, so we don't care, right? I mean, they're finite, and they will have some order. Each one we would have some cardinality, right? So this number is fixed for each one of them, and then there's a representation of minimal dimension, but that's it. There's a bound there. Okay, so we don't have to worry about these groups, fortunately. And so we solve the problem for the case G is a simple group, a finite simple group. And then there are some arguments involving group theory. If G is not simple, we take a minimal normal subgroup, and there are results saying that this must be the power of a simple group. So n must be some power of a simple group, and it must act irreducibly by that lemma before, because it's a normal subgroup and of G, and then we have and so we can use the classification again. I mean, it's a power of a simple group. We can use these results for powers of simple groups also. And finally, we look at G mod n, and I mean, G is going to, there's an exact sequence like this, and so we understand this, and we have to understand this, but this, I mean, n is a normal subgroup, so the elements of G normalize n, so they induce outer automorphisms of n. So, and n is a power of a simple group now, and so we can understand this also, and we can obtain an estimate of this from that, and so after some work, we get an upper bound for this number, and this is the proof in the case of G is finite. Okay. Any questions? Okay. So I'm going to move now to the last part of the talk, which is the case G0, the identity component of Gx irreducibly of n plus 1. And here we use Riemann geometry more. Well, we use the Bishop-Gromov theorem before. Now we use other arguments. So first we need to reduce. I mean, G0 acts irreducibly. Of course, J is also irreducible, but I mean,
No, no me muero.
okay. So this is right. This is a compact connected group, right? I mean, there's a torus part eventually,
Te vas al suelo.
which is going to be only a circle
Te
because
vas
the
al suelo.
representation is reducible anyway. At
Si
most a
quieres estar aquí, te
circle,
vas al suelo.
and then maybe this is there, and maybe you have some simple just compact simple Lie groups, and this can be present or not, and so the representation is going to be a tensor product of representation with these factors, and tensor products are really easy to deal with. And since this is compact also in G normalized G0, the normalizer of compactly group is also easy to understand. It's, I mean, the automorphism of outer automorphism of compact groups are finitely many, right? So really, G is going to be a uniform finite extension of a compact connected simple Lie group. So what I mean is that since it's only a uniform finite extension, the diameter between quotients of this sphere by G and by G0 are comparable. So we can assume that G is even connected. And yeah. And then we have connected orbits, and then we invoke a result of mine with a master student that I had a few years ago, where we studied a local problem. In fact, we showed that if you take any representation of a compact Lie group in a Euclidean space, you look at the orbits in the unit sphere, you can always find a point which is kind of related to the highest weight vector of the representation, such that the orbit through this point has a focal radius bounded below by universal constant. So I have to explain what is the focal radius. So it's an infinitesimal thing. I mean, because you have a submanifold, could be in the sphere or in Euclidean space. You look the normal exponential map. The normal exponential map. So you map normal vectors.
No. No?
You take this normal geodesics, right? And you take the endpoints of these normal geodesics. And the focal point is when nearby normal geodesics like this converge to a point. This is a focal point. So they are critical points of the normal exponential map. Critical points of the normal exponential map of the submanifold. And the focal distance is this distance here, right? So the focal radius is the infimum of these focal distances as you go along the submanifold. So what we are saying is the focal radius cannot be very small. So these geodesics, they cannot converge very close to the submanifold for orbits of representations of compact Lie groups. And of course, this is infinitesimal in some sense because we have to differentiate this exponential map into critical. Sorry, these are critical values, I said, not critical points, critical values, right? Yeah, critical values of the normal exponential map. These are focal points. And so we have this bound with focal radius. How does this help, right? Okay, this is what I said now. Well, we have the normal injectivity radius. This is another thing. I mean, the normal, if you have n here, it's an orbit. The normal injectivity radius is the radius of a maximal tubular neighborhood. So this is a tubular neighborhood. So what's a tubular neighborhood? A tubular neighborhood is where the normal exponential map is a global diffeomorphism. So if you take a point here, in this tubular neighborhood, there's a unique normal geodesic reaching this point, because it's a global diffeomorphism. Of course, if we have critical points of the normal exponential map, critical values there, it cannot be a global diffeomorphism, right? So therefore you have this inequality. I mean, here is where it is a global diffeomorphism, it's a local diffeomorphism here. So it's smaller than or equal to the focal radius. So we have this inequality. But then we have another inequality also. We can show something like this also, right? So something like this. And I'm going to explain how to get this this inequality. And if you combine, so we know that Fn is bigger than delta, right? So we have this inequality, And then if you use this one, you get this one. And finally, the diameter is bigger here, right? Because inside the tubular neighborhood, if you take a point, there's a unique normal geodesic here, reaching this point. So if you look in the orbit space, this orbit and this orbit, the distance is precisely the length of this geodesic. So this distance is precise. So in this length, you can go up to the injectivity radius. So in the orbit space, you get at least distances like this. So the diameter is going to be at least this, right? So we only have to explain now how to get this inequality. Okay, and then I stop. So, right. So let me draw here an orbit P, and then we have a tubular neighborhood here, radius I of n, and we know that I of n is less than Fn. Now suppose that it's really smaller, right? So how small can it be, right? We're going to show that this is the smallest it can get, right? So if it is small, what does it mean? It means that, see, I mean, we have not reached yet critical, we don't have critical points, we don't have critical values of the normal exponential map, right? But already we reached this injectivity radius. So not because of a critical point, but because the exponential is not injected. So it means that you took some normal geodesic here, and far away there was another normal geodesic, and they meet before wait, what is, yeah. I mean, yeah, my picture should be like this. We meet here, right? Oops. They meet here. But I mean, focal points, they happen, outside, right? And this P and Q these are geodesics far away, starting from points far away one from the other. Yeah. So it's like the normal exponential map is not injective, right? So in this situation, so the length here is going to be this number, the length here is going to be this number, they have the same length. And then we argued that there cannot be a corner here. Because if there was a corner, you could shorten somehow these two geodesics and get that they find other geodesics that meet even before. And the normal injectivity radius would be even smaller, so there cannot be a corner there. This is a variational argument for the length functional. Pretty standard, I mean, Klingenberg idea. So there's no angle, they meet smoothly here. So Now we can say that this geodesic, say, starting at Q, is smooth geodesic like this, and it reaches P on the other side. And then we have to go back to the result of Saturnino. The nature of this point P is very special. Maybe the nature of this, yeah. Maybe we look in the other way around, this orientation like this. So the nature of this point P is special in the sense that, well, it's related to the high state vector. So there are some arguments there involving representational theory which show that the isotropy group at P, the elements that fix P, they do not fix. Well, we can find an element, a one parameter group fixing P, but not fixing this normal direction. Okay, so we use this one parameter group of isometers to move the geodesic. So it's going to move, deform it. So deformation like this, fixing P. So this shows that P is a focal point now of M. Because we found this one parameter family of normal geodesics meeting, converging at P. Therefore, the focal radius is at most the length of this geodesic, which is, that's what we wanted, right? Exactly. So that's the argument. And, well, I have only here another slide which are questions for further research. But, I mean, you can ask the same, replace the unit sphere by a compact symmetric space. And ask the same question, if we can make the diameter of a non-trivial quotient arbitrarily small, right? But you need to fix the rank of the symmetric space, otherwise there are counterexamples. And you can ask similar questions for hyperbolic manifolds. I mean, the sphere is like constant curvature 1, right? If you take your hyperbolic space, constant curvature -1, and take quotients of this, you can also study the diameter of quotients. And these are singular remanifoldations, are generalizations where you don't have a group, you have just a foliation. I mean, in the case of a group, you have a foliation by orbits, and in this case, you have a foliation with some properties, but there is no group. And so you can ask these questions, but of course, the techniques needed to study these problems, these two problems are going to be very different. But this problem may be not so much different from the one we studied. And so, yeah, I'm going to stop here. Thank you.
Thank you, Danny. Thank you very much. Well, time to question now for question and remarks.